Today we're going to talk about solids and liquids. Now, the most important thing in determining whether something becomes a gas, a solid, or a liquid is how much intermolecular forces there are between the molecules. Now, what are intermolecular forces? Intermolecular forces are the forces of attraction that may exist between atoms and molecules of a substance due to electrostatic phenomena. Key here is the first prefix of INTER. That means between. So intermolecular means forces between the molecules. This has to be distinguished between intramolecular, INTRA, which means forces within the molecule. So in determining the natural state or phase state of any particular substance, the important understanding is those INTER, molecular forces. Transitions between solids, liquids, and gas of a substance occur in conditions of temperature and or pressure that favor certain associations or associated changes in intermolecular forces. And as I said just a minute ago, please keep it straight between intramolecular forces and intermolecular forces. Intra is the force that keeps the individual molecules intact. Intermolecular forces hold multiple molecules together and determine many of the properties of the molecules. Condensation forms when water vapor is cooled in air enough to form a liquid, such that the intermolecular forces are such that a liquid forms. So A shows what happens around a glass, and B shows the formation of fog in natural circumstances. Now, there are various types of intermolecular forces, and the first type I want to talk about are called van der Waals forces. Van der Waals forces exist and are all the attractive forces between neutral atoms and molecules, So gaseous butane here is compressed with increased pressure until the storage compartment, within the storage compartment of this lighter, and it results in a condensation of butane to its liquid state. Now, as soon as the butane is allowed to escape to normal atmospheric pressure, it becomes a gas and is lit and performs its function. Now, another intermolecular force is called a dispersion force. The dispersion force is a weak force. It's also known as a London force that results from electrostatic attraction between various atoms. So a dispersion force can occur in the situation where you have significant polarity, such as this, or when there's not very much polarity. Generally, dispersion forces are seen because instantaneously electrons are maldistributed and result in an instantaneous dipole, which comes and goes as rapidly as possible, or as rapidly as the movements of the electrons that are being distributed asymmetrically. This instantaneous dipole can and should not be confused with a real dipole that occurs in a polar molecule. An induced dipole is an instantaneous dipole that occurs because a neighboring atom interacts with the molecule and causes a maldistribution of the electrons. Now, as I said, this all relates to the uneven distribution of electrons, which result in temporary dipoles, which lead to weak attractions. Dispersion forces result from the formation of temporary dipoles, as illustrated here in these two nonpolar diatomic molecules. These are nonpolar molecules, but because of instantaneous unequal distributions of electrons, there are very weak forces that are called dispersion forces. The larger the molecules are, the more these temporary dipoles occur. And therefore, the larger the molecules are, the stronger the dispersion forces. Make sure you remember that, because when you're comparing the boiling point of, say, several large or several nonpolar molecules, the differences in boiling point can many times be the differences in the size of the molecules. So here's a question. Order the following compounds in the group 14 elements and hydrogen from the lowest to the highest boiling point. If you are to do that, you see that SnH4 is the largest and thus has the highest boiling point. Now, the boiling point is still very, very low because these forces are very weak. But you can see as the size of the molecule gets smaller, the dispersion forces get weaker and weaker, and the boiling point gets lower and lower. Polarizability is the measure of how easily or how difficult it is for another electrostatic charge, for example, a nearby ion or polar molecule, to distort the molecule's charge distribution. So it's another way of saying how inducible the dipole is. The more inducible, the more polarizable, if you will, and the stronger those dispersion forces. Now, another important point about dispersion forces is the fact that the strength of dispersion forces increases with contact area between molecules. Now, these three molecules all have the same formula, so they're all of the same molecular size, but they have different shapes. Neopentane is a conglomerate. Isopentane has one side chain, and N-pentane is a straight chain. And because N-pentane has a greater contact area, that it causes it to have a higher boiling point than isopentane, which has a higher boiling point than neopentane. So the strength of the dispersion forces increases from left to right because the contact area increases from left to right, and while the size of the molecules are all the same. Now, when you have a true polar molecule, you have much stronger forces called dipole-dipole interactions or dipole-dipole attractions. This is an attraction between the actual formed poles of the polar molecule with each other, so that the negative pole of one polar molecule is attracted to the positive pole of another polar molecule. This is an example of hydrochloric acid and shows that these molecules will line up such that the positive pole of one is close to the negative pole of another. And these forces are much stronger than the previously discussed dispersion forces. This image shows two arrangements of polar molecules, such as hydrochloric acid, that allow for the attraction between the partial negative end of one molecule and the partial positive end of another molecule. Now, a special type of intermolecular force is called hydrogen bonding or hydrogen bonds. Hydrogen bonds occur with certain molecules, and some people say that they represent extremely strong dipole interaction. But most people talk about it as a separate category of intermolecular force known as hydrogen bonding. Hydrogen bonding occurs when there are interactions between fluorine hydrogen, oxygen hydrogen, or nitrogen hydrogen. And these are very strongly attracted to each other in nearby molecules. And this particularly strong dipole-dipole interaction leads to very high, comparatively high boiling points in these molecules. The water molecule here participates in significant hydrogen bonding, and this is one of the reasons why the boiling point of water is relatively high compared to other solvents. Now, if you were to look at groups 15, 16, and 17 on the periodic table, so this is the various hydrides of those various groups, you notice that The ones that are not representative with hydrogen bonding have very low boiling points and follow the rule regarding size, comparative size, in terms of showing their various boiling points and their strength of bonding. But the hydrogen bonding that occurs with this one group, water, hydrogen fluoride, and ammonia, in period 2, throws this entirely off because of the hydrogen bonding. And the boiling point of these substances is considerably higher than one would predict based on dipole-dipole interaction. Now, an important molecule that takes advantage of hydrogen bonding is the DNA molecule. The bases that occur in the DNA molecule have hydrogens and oxygens extending off of them, and the interaction between the two DNA strands is a hydrogen bonding interaction. And so it is a strong interaction that holds the double helix together. And here is a more close-up view of what I was just talking about. In the middle, where the bases occur in the DNA molecule, you see that the ammonia, or the NH2 or NH, interacts with oxygen or interacts with another nitrogen. And these represent the bonding forces that hold the two DNA strips together. And these base bondings have to be broken apart in order for the DNA to open. And the reason these are complementary pairs is you can see that in one situation you have 2 hydrogen bonds, that's between thymine and adenine. In the other you have 3 hydrogen bonds between guanine and cytosine. Therefore, guanine would not bond with adenine as well because one has 3 sites, the other has 2. Conversely, thymine would not bond with cytosine very well for the same reason. Now, another property of liquids is something known as viscosity. And viscosity is the measure of a liquid's resistance to flow. Now, 2 examples of liquids that have a higher viscosity are honey and motor oil. And both of these, as you know, flow quite slowly depending on what you're comparing it to. But compared to, say, water or other more normal liquids, these two flow very slowly, which means they have a high viscosity. Another property of liquids is something known as surface tension. Surface tension is the energy required to increase the surface area of a liquid, or it's the force required to increase the length of the liquid's surface by a given amount, which is why it's called surface tension. And surface tension is controlled by what are known as cohesive forces. Now, we've mentioned the term cohesion and cohesive forces before. In a liquid, these are the forces between molecules of the same type. And what we see in the picture here is some water droplets on a web, and the water holds together in these little droplets by means of cohesive forces. And if you want to push apart or pull apart these molecules of water, you have to overcome the surface tension of the water. So the attractive forces are what result in the spherical shape of a water droplet. The spherical shape is assumed because this minimizes the surface area. And a sphere is the most geometrically economic in terms of energy of the various shapes that a water droplet can assume. Cohesive forces hold this sphere together, and adhesive forces, that is the forces between different kinds of molecules, are what keep the droplet attached to the web. Now here is an example of surface tension at work. You have a bug known as the water strider, and this bug can walk on water, as it were, because the area with which its foot encompasses is large enough that the force required to separate the water by the foot is greater than the actual weight of the bug.